equation for the density was partial derivative or the functional derivative of E rho equals mu. And I had also said that you can show, and in fact I had discussed it quite in detail, that this can also be converted to Born-Sham equation, which is minus 1/2 del square plus the external R plus the RTR is something called the V exchange correlation R phi I equals epsilon I phi I, and the only information, because we said this is equivalent to the Euler equation, see, the only information it gives you is rho R phi I R square occupied. Okay, that's the only information we get, nothing else. So just a note. So this is a non-interacting system because this is all, there is no interaction in it, right? The only information it gives is this. What will be the wave function? It will be a Slater determinant of the occupied orbitals, right, by and this is not the wave function, not the wave function of the system. This is an auxiliary system that through phi gives me rho R. That's all, nothing else. All right, and once you get rho, it gives you the energy E rho. This is the root of Born-Sham. All right, it also gives you epsilon i's. Right now, this is an auxiliary system, so you have these epsilon i's filling epsilon 1, epsilon 2, epsilon 3, and so on, and they have no meaning. They have absolutely no meaning. They're just appearing as some numbers. Whereas, if this was a truly non-interacting system, like the hydrogen atom or something where nothing is happening, then each one of these will be renewable energy. Right? Epsilon I will be removal energy from ion orbital for a truly non-interacting system. Not anymore. This is an auxiliary system, doesn't have any meaning. Alright? Because this is a virtual system. However, epsilon max, the uppermost, is a meaningful quantity. Let me just say that, what it is. Now, in the true theory, I have delta E, delta rho equals mu. And if you calculate, if I change, once I have calculated mu, if I change the energy, calculate the change in the energy through this derivative by changing the density. If I do that, this would be equal to mu times delta n. Right? And therefore, you can write mu is equal to dE dN V external. This is a chemical potential. And what is this? Is the difference in E ground state for 2 n and n plus delta n divided by delta. Right? So this is the minimum energy required. So this is like the ionization potential or electron affinity if you add. Right? So if I take delta n to be minus 1, that means I am removing an electron. Right? Then it will be E n minus 1 minus E n divided by n minus 1 minus n, which is minus the ionization potential. So if you remove an electron, mu should come out to be minus I, and if I take it to be plus 1, it will come out to be electron affinity minus the electron affinity. Alright? That's that. Now in the same manner, if you look at, and I'll give you this more rigorously. If you look at this system, the virtual system, right? The minimum energy from the non-interacting system that you require to remove will be epsilon max. You remove it and that's the energy change. Right? This is a non-interacting system. So this therefore is mu or KS system. Anything else has no meaning. Epsilon max has a meaning as mu. But the way we constructed this and the cone sham, mu was the same because this we wrote as delta ts, so delta rho plus V external plus V Hartley plus Vxc DFT. So mu is same by construction and therefore epsilon max is equal to minus I for removal of an electron and minus A for n. So if you do a true cone sham system calculation, the uppermost eigenvalue will give you minus I. Alright? Okay. So these are the exact properties. Now, one does not know what EXC DFT is, therefore one has to approximate. So, ES rho is not known, EXC DFT rho is not known, and EXC rho. As a functional rho, it's not known. However, in cone sham theory, ES rho is phi I minus r to the square from that. That's how we constructed it. So, why I'm saying this is, I've given you in assignment 2 problems. One is related to this. So, what approximation one takes for this is T Thomas Fermi rho, which is 3/10 3 pi square raised to 2/3 rho r raised to 5/3 dr. So I've asked in the assignment to solve a problem using Thomas Fermi approach. And here something called the LDA, local density approximation, in which Ex, these are derived from homogeneous electron gas, where you can derive this exactly as minus 3/4 3 pi square raised to 1/3 integration rho raised to 4/3 dr. And EC, I've given you an assignment, do an interpolation formula, get your answer. So use that interpolation formula, which is of the form some constant A and B, which you derive R as rho R. Okay, so this is the one approximation. This you are deriving. Okay. This is your function. You created it. Okay. So one problem based on this, one problem based on this. Alright? Okay. So this is as far as doing cone sham is concerned. And now after that, a lot of business is developing this. Right? You do the local density approximation, then you include gradient corrections and things like that. And I'm really very happy that the DFT group out here has made really nice strides in developing new functionals. Right? The Samal's group has done it, and he being my student, I feel very proud about it. So that's something I must say. Alright? So in fact, after coming here, I've gained weight because I'm so happy. Okay, so this is as far as the Quantifying theory is concerned. This is as far as the development of the functional system is concerned, and you get some practice with this. And it will also tell you what all happens. Now I'm going to go into some mathematical properties. Okay, this is a well-known technique, and then you can keep developing functionals, you can keep doing things, and be happy with them. Sometimes answers are good, sometimes they are not, but we have at least gotten a handle as to how to do it.
So pink color is not visible properly.
Green color?
Pink one.
Pink one?
Yeah.
Pink one I thought would be nice. I like pink color, but anyway I will not use it. Or we use this and this. Okay. Let's get to some exact. So exact properties so far. If one could do the Quantifying system is giving you rho, which is through summation phi I r square. It is giving you E rho, which is phi I t phi I sum over plus integration V external dr rho bar Vr plus E hat t plus E h t correlation, and in addition you are also getting I, which is equal to minus epsilon max. I'll derive it even more interestingly later. Alright, so this is what we've got. Now we are going to explore some more subtleties of this. So I'm going to spend some time on universal function. And this will tell you how this map can be done. The definition of universal functional and map from rho to psi or rho to the external. And since it's a Quantifying system, we take the V to be V non-interacting, rho to be Quantifying. Okay? So let's see. Now see, usually what do? You say that when I want to calculate the energy, it is equal to the minimum of look over all sides and to T plus VEE plus V external psi. That's search over all sides. Right, that's the variation principle of the energy. And no wonder I feel tired, you didn't give me the mic today. And from here, let's ask the question, if we restrict the search to psi such that psi gives 0, I restrict myself. I'll say I look for this psi, so I have this entire Hilbert space, all kinds of antisymmetric wave functions, psi 1, psi 2, psi 3, and so on. I'm going to now restrict myself to those functions. This color is different, so only those where in restricted search, psi 10, maybe psi 11, and so on. All these wave functions give me rho r. Okay? Suppose I could do that. Because I have a huge computer, I tell it, go do the search. Alright? And then I restrict myself to only these. Then, E would be equal to psi min psi T plus VE psi plus V external or some V external, whatever it is. Yeah. Right? And if I'm searching over all these sides that give me the same rho, this is constant. This doesn't change. So if we find psi such that psi gives you rho and do minimum of psi E plus VEE psi, I found the ground state wave function. So that's the minimum possible energy. Second term is constant. So gives from rho. Yes.
So what do you specifically mean when you say look for only those sides which give us rho?
So I'm given a rho, I'm given a density rho. Somewhere experimentally or whatever, I do the exterior fraction and find rho. Then I say I'll pick only those wave functions. Now there will be zillions of wave functions that give me same rho. And I'll pick all those. And I'll plug everything into this. And say whichever gives me the minimum value of that, that's my psi ground state. So I found from rho to psi ground state value. Without worrying about the external potential. Right? That's von Goldbaum theorem. Alright? So this, and I've also found the universal functional f rho, which is minimum of psi T plus VE psi gives me rho. So given a rho, I found the map from rho to psi, and I have also found the corresponding f rho. That's the universal function. I did not have to know what V external is. Right? This is known as constraint search. DV's constraint search approach. Not only that, I can also find a Kohn-Sham system through it. How do we do that? Remember what is the Kohn-Sham system? Kohn-Sham system is a non-interacting system. So if we say find phi Slater determinant such that these phi give me rho and minimize phi SD T phi SD, because Kohn-Sham is a non-interacting system, there is no electron-electron interaction. This is the Kohn-Sham system. And this minimum is your DSO. Any questions so far? This is the real nitty-gritty mathematical aspects of the theory. Alright? Any questions? Okay. Now you may say, fine, you found f rho and you know all this. Can I really find Kohn-Sham system like this? And the answer is yes. And I'll give you one method, but then we have generalized this, and I'll tell you that method also. So think of this. You can also say, I'm minimizing phi I, p phi I, and p operator happens to be minus 1/2 del square summed over I. Right? This is what I'm minimizing for a Kohn-Sham system. Right? Such that summation phi I square minus rho r, which is fixed, is 0. I'm doing that. So what am I doing? I am taking a variation of this and making it equal to 0 with this condition. What this condition means in return, because this is fixed, is delta yi star plus phi I star delta phi I is 0. Notice when we do the normalization, it's the integral, but I want this to be 0 at each point, so this variation itself will be 0. First one. Is that point clear? When you say normalization, right? When you say phi I is 1, then it is the integral delta phi I star phi I plus complex conjugate, which is 0. But I'm doing more than that. I'm wanting at each point there should be no variation, because I want orbitals to be such, even if I'm varying it, that the density remains the same. So let's do that. This variation would come out to be delta phi I summed over I minus 1/2 del square phi I plus phi I minus 1/2 del square delta phi I, right? Should be 0. Normally, if all delta phi i's were arbitrary, then we will say that half del square phi I should be 0. If these were completely arbitrary, but they are not, they satisfy this condition. Right? So if we say minus half del square phi I is equal to, I'm just writing it minus sign for convenience, minus some VR, some function, and I'll add a constant epsilon I. Okay? Even if this was so, right? What will be each term? This will become this term. Would become integral phi I star VR plus epsilon I delta phi I, right? Right now, some constant, let's leave this, this is for normalization, plus integration, a complex conjugate. Okay? Now at each point, phi I star delta phi I summed over is 0, is summed over. So even if I have a function VR, it will still be 0. So this is the most general condition. And the normalization of phi I, this becomes this. That's the Quantifying equation. Okay? So I can derive the Quantifying equation through Levy's constraint search also. And how do I practically do it? In reality, suppose I'm given some density. Then I can use a condition that enforces this and then invert the density to get the Quantifying system. And I'll talk about that in a minute. But I'm saying right now, let me just go back to the universal functional f rho. Okay? And I want to derive certain properties of it. Remember, f rho is something which is being defined as a minimum. Alright? Now we'll do a little mathematics and say, so before I do f rho, on the side I'll do something for the energy. Suppose I have, and whatever I say for interacting electrons is true for non-interacting, obviously. It's less complicated. Suppose I have a system, right, with potential V1, another system, the same number of electrons with potential V2, alright? Then, energy of a system with lambda V1 plus 1 minus lambda V2 is necessarily greater than lambda E V1 plus 1 minus lambda E V2. The lambda lies between 0 and 1. This is called the concave property. Why concave? If I were to plot E for V, suppose representatively there was one V1 out here, another V2 out here, then the energy would be necessarily this. Whatever is in between, okay, satisfying this. Okay, so this I'll leave for you to prove. It's very easy using variation principle. Let me just quickly do it. So how is it done? Very straightforward. This, suppose the wave function is psi, then I have h v1 plus this lambda v2, right, with respect to psi is equal to, I can write lambda t plus ve plus v1 plus 1 minus lambda t plus ve plus v2. That's exactly the same Hamiltonian. Because lambda t plus 1 minus lambda t gives me the kinetic energy operator, lambda ve plus 1 minus lambda e gives me this, and third one is this. And this I'm taking with respect to psi. Now the wave function for t plus ve plus v1 would be different from psi. So by variation you can split it. Alright, so this is just to give you an idea. Now, what one wants in F rho is that F rho should be convex with respect to rho. And what it means is that you should have F lambda rho 1 plus 1 minus lambda rho 2 should be less than lambda F rho 1 plus 1 minus lambda F rho 2. What it means is, symbolically, if I have rho 1 here, rho 2 here, then it should be something like this. Is that okay? Because lambda F1, lambda F2 will go along this line. This line would be lambda F rho 1 plus 1 minus lambda F rho 2, and you want it below that. Here, line, this line was lambda EV1 plus 1 minus lambda EV2. So it should satisfy the convexity property. It's a nice property to satisfy if you want it to lead to a minimum. Okay? And this is done if you define, it's just to go the other way and if you define F rho to be maximum, or in pure mathematical terms I call it supremum, with respect to V of calculate E for that V, and for a given density calculate VR rho R here. Now since I did that, I'll leave it as an assignment for you to leave that F rho defined this way satisfies this. Okay, let it be an exercise for you. So it's a okay. So when you define it like this, you can show that it satisfies the convexity property. Alright? Now, what does this tell me? So what I'm doing is, given a density rho, I'm solving the problem, exactly, for different V's. And finding this. The V that maximizes this is the correct V for that rho. So, given rho, V that maximizes EV minus VR rho R is the V corresponding, and F rho is also calculated. Any questions on that? So I've given you two schemes. One is F rho psi min psi E plus VE psi, right? And F rho is equal to V max. I'm not putting any restriction of this giving rho. E V minus V rho. Alright? Now I promised that I'll tell you that there is a map. So I've given a map from rho to psi to this. And this gives me a map from rho to V. Also, take a density, solve the Schrodinger equation, 1/2 rho square plus V, and then that means like E plus VEE plus V external, that will solve the many body wave function inside. Okay? And this gives me an EV. Calculate EV external minus V external rho R. Yeah. Keep doing it. Keep looking for V external until you maximize this. The moment you maximize that V external corresponds. I could also do a Kohn-Sham. For Kohn-Sham, solve P plus some V local, let's call it S phi later determinant of phi I equals epsilon I phi I. Right? Calculate summation epsilon I is the Kohn-Sham energy that I told you yesterday. Right? That's for this Vs minus integration Vs rho R dr. And maximize with respect to V. So that V S corresponds. If you solve for the non-interacting system, you found the Kohn-Sham potential. If you do with the interacting system, you found V external. So I established two maps. I established map from rho to psi. I established map from rho to V. Okay? And these are practical. These are done with using these. You can actually find out for some systems where rho you can be calculated by many body calculations, say small atoms, small molecules, or X-ray diffraction factor, X-ray structure factor of solids. You can invert it and get this. So this is called as the Kohn-Sham inversion problem. Just quickly, how it becomes very effective. Let me just do this example of finding the quotient. And it is an iterative process because you're just doing a searching of V. So suppose at some iteration I have a potential VI. I iteration. I have VI. Alright? I have VI and I want to find VI plus 1 such that summation epsilon I minus VI plus 1 I plus 1 rho is greater than summation epsilon I minus integration VI rho. If I keep doing this, I'll finally hit the maximum. Is that clear? If I keep finding a scheme where I update my VI to next iteration and that keeps increasing, I'll finally hit a maximum. And the moment I hit maximum, I found my V. Is that okay? So that means summation epsilon I plus 1, I mean this is I plus 1 iteration, not I, so I plus 1 iteration. Okay, this is, I should write iteration number on top. Iteration number on top. And this is J minus epsilon J I, right? Minus integration VI plus 1 minus VI rho is equal to 0. This is a given rho, so let me call it 0. Is that okay? This is a given rho. Given. Is that okay? Now, if I change VI slightly by perturbation theory, I can write this as integral delta VI, so VI plus 1 minus VI, mod phi I square added over J, so that gives me rho R at the I integration. And then I have minus integration VI plus 1 minus VI, rho 0 is written. And this gives you VI plus 1 minus VI, rho I minus rho 0, PR greater than 0. If I make a correction scheme so that this is ensured, and I keep repeating my calculation, at each step I keep updating VI, I'll finally hit the 2 quotient. And that's a lot of interest in this because I want to know if I could calculate the exact density somewhere, what is the 2 quotient. Now, one way to do this is a weak condition. Strong condition would be just make the integrand greater than 0. Make the integrand greater than 0, then anyway the integral will be 0. Right? Now this makes sense. Suppose at ith iteration, Vi is greater than rho 0 at given point. Next point I want to bring Vi down. I should increase the potential. I'm increasing the potential next. So that the product is less. If it is less, I should decrease the potential. So this should be negative. That again is the same. So one example, for example, could be that I take Vi plus 1 minus Vi to be rho I minus rho 0, etc. And I keep updating. Okay, so we can keep doing this. This is known as rho 2 Ks inversion, and there are different codes. There is a now there is a code available which is known as N2V. This type is group is given by the group from Purdue University. Okay, and we have done a lot of work with this. Okay, now this we have given one map. The other map is through constraint search. That also can be done, and I'll leave that for you to read, those of you who are interested, which is known as the Zhao Morrison Bar or ZMP method. And we've been able to generalize this whole thing We have shown how this is a universal class, this is a universal class, so we have two papers on this. One is on the universality of inversion methods, another is the relationship between Levy's constraint search and DFT. Okay? Now I'll take any questions that there might be. I hope this answers certain questions about universality that you asked.
From a computational complexity standpoint, from my observation of this, it seems to me that this iterative process would be a better thing to handle.
Both are iterative.
No, in terms of the complexity, in the sense of how fast it will converge. So I was thinking, say if you are doing a search, let's say,
So if you do it iteratively only.
but the convergence rates are the same. I mean,
Same for as what?
the convergence rate to when you stop your algorithm.
So convergence vis-a-vis what? What do you
Okay,
want?
so here, for example, you have a convergence criteria where you will it's sort of go to maximum.
Yes.
In the sort of the constraint search,
You do a minimum.
yeah. So the
Yeah, roughly the same. Roughly the same. Constraint search, it becomes a little difficult because in constraint search you are also trying to satisfy a constraint. Since you asked me why constraint search is difficult. So in constraint search, what it is, I'll give you one condition, how one is in part. So if I want to make sure that rho obtained is same as rho 0, that means, and you can show them from electrodynamics, rho r minus rho naught r prime times rho r prime minus rho naught r prime over r minus r prime dr dr prime is 0. You can show from electrodynamics the 0 means each term is 0. Okay, this is from Laplace equation. Now, if I want to apply this condition, I am doing minus 1/2 del square phi I, and for this condition I will apply Lagrange multiplier and take the derivative and give me this condition. And prove orthonormality of phi. Alright? Now the certainty comes that when you are approaching rho naught, this quantity becomes small and small. So lambda has to go to infinity. So you do this calculation by increasing lambda each step. And you go through this maybe 1,000, 2,000, 3,000. So this is a little more subtle and difficult to converge. And this is easy. And again here you can choose different functionals depending on your system. If you have a molecule of certain dimensionality, certain shape, you may want to choose different functions. In fact, we did one with the random search also.
So how easy is it, as you said, practice Levy constraint. So when you say that I limit my search to a set of sites which gives me given density, it's still exponential reverse space, although we have sort of thrown a lot of exponential stuff.
Yeah. So the thing is, how do you practically do it? I'll show you one practical way.
That's sort of.
Yeah. So, and you're slowly converging towards that. Okay, so you start from this area, and then you converge to smaller responses.
Brute force would be bad.
Huh?
Brute force would be bad.
Yeah, even in the best computer. How do you construct it in the wave function? Right? And by the way, this people have also done this, and in fact, I'm doing with somebody. You can take Hubbard model, you can take TVA model, this, that, and that.
Yeah.
Gives you some insight.
Yeah, we have to sort of carry these over to the Fox space and sort of clean the Fox space in the second.
Yeah. So I focused on universally functional, given certain of its properties, and it's people say, why are you doing all this math, convergence, convex, how does it help? It helps. It has given you a practical way of doing inversion. And inversion is a tough problem. It's a very, very tough problem. Okay, since there are NSC students also here, what is the inversion problem given in Landau's book? Go search it. Okay, now that this is done, now I want to focus on that mu, the chemical potential. Alright, and I'm looking for mu. Remember we said delta E, delta rho is mu. I can also write this as delta T rho over delta rho plus V external plus V heart free plus delta EXC. I'll call it quantum mechanical, delta rho is equal to mu. And then we have the cone sham, delta TS rho, delta rho plus V external plus V heart free, since it has to be the same, so V heart free remains the same, plus delta EX. See, let me call this VXC, because that's the way we refer to it. Mu is the same. Okay? The starting point is this, and I just showed you earlier that this means partial E, partial N is mu. Right? And what I showed you earlier through this is that I showed you three finite difference formula. That mu minus I or minus A. This is for and number of electrons. You know, if you are removing, so this is removal, this is adding. And electrons. Now this is finite difference, right? And what we want to do is, if I want to be rigorous, I should be able to do something here. Now there is a problem in this also. If I should be able to define mu rigorously. I should define E for fractional number of electrons. If I do that, then only I can write DED, and otherwise I remain in finite difference. And why do I want to do that? This is a very simple thing. Suppose I take sodium atom. And a chlorine atom. Right? And I define some mu. I'm calling it chemical potential. There could be a transfer of electron from one to the other. Lower the energy. Right? If mu, that's how you define mu. How do two atoms far apart, stop that transfer? How does mu exist? I want to answer that, and we want to answer this. Okay? Now this brings out a lot of stuff in DFT, because this is also ultimately related to the way you get band gaps in semiconductors. It's a very, very important concept. Now if you want to define E for fraction number of electrons, so fraction number comes from the statistical mixture. That is the only way I can have a fraction number of electrons. I cannot have it any other way. Electron is either 1, 2, 3, 4. So I have to have a statistical mixture. So what you do is, and I want it at t equals 0 because I'm restricting to ground state. what I want to do is have probability P for the I number of electrons such that summation of this probability is 1, such that summation I, Pi is equal to that number that I want, let's call it x, so that it doesn't look like anything. IPI is x, and I want to minimize summation Pi should be I'm asking a very funny problem. This is a funny problem because you see E is depending. So let's call this Ex. E is depending on Pi linear. Right? How do I minimize the linear thing? Linear thing is always minimum or maximum at the end points. Right? So what am I looking for? I'm looking for, given this number, what should it be? Right? So, and this Pi could be anything. Right? Pi are restricted to these. I have shared 5 or 6 pages with you. I think I've sent this, where I've given the long derivation. Okay? And there I've argued a very, very long way that when you do this, the only way you can do this, if I have, so go through that derivation and maybe one of those next lectures we can discuss that derivation if you don't understand something. But the only way you can do it is for the number x between, say, m and m plus 1, okay, then only Pn and Pn plus 1 are non-zero. The rest of Pn's are 0. So you mix only 2 states. You can prove it. Okay? And other thing about energy is that E n plus 1 minus 2 En plus E n minus 1, okay, is always given 0. You can see this, what is this? This is En minus 1 minus En minus En minus En plus 1. This is ionization potential, this is electron affinity, this is always the relativity of all systems. And that makes sense. Either it will be equal or 0. If there's an interacting system, as you increase the number of electrons, the electron interaction increases, and therefore removal becomes easy. Because there's a lot of positive energy you're pumping in. So under these conditions, what you have is that the energy Ex, and I'm going to call that x as m plus f, where f is a fraction, is going to be f of E n plus 1 minus f of En plus 1. Okay? The density for m plus f, now I'm taking that as a mixture, is going to be rho m plus 1 minus f. The other way is the other way. 1 minus f and this is 1 minus f and this is f. Rho of m plus 1. Okay, all quantities are defined this way. Okay? And if you plot this energy, then it comes out to be, suppose this is m. This is m plus 1. This is m minus 1. And here is the energy, and I said it's always with respect to when it's convex functions. This goes lower, and this goes even like this. So it varies linearly. And for m plus f, here is the energy. For m minus 1 plus f, here is the energy. There is no other choice. fixed. That's it. Okay, so energy value is like this. Now any exact functional energy function must give this. If it doesn't, then there's a problem. It's an approximation. But I've given you a problem for non-interacting system where you find that Thomas Fermi approximation doesn't give it. Now, therefore you see that I've defined very carefully right here. This is EM minus 1, that's right, N because N, everybody uses it. N is NP. So slope out here, this is difference between En minus 1 and I, this is minus I. Slope out here is minus A. A is the ionization potential for M plus 1 system. So you see, now we have shown rigorously that this is how it acts. Okay? Now given two systems, suppose sodium and chlorine. Suppose I want to remove an electron from here, it will be chemical potential is minus I and chemical potential out here is minus A. So out here chemical potential will be this and out here it will be this. Electron cannot go from lower chemical potential to higher. They remain neutral if they are far away. Okay? On the other hand, if I want to take an electron from here and bring to Na, then it will be ICl, minus ICl and minus Na is again up, so it cannot go this way. So by changing mu as a fractional number of electrons, receiving and giving, its behavior is different. You keep the far away systems neutral. And this is known as the size consistency problem. So for size consistency, it is important that exact function behave like this. I remember I had touched upon size consistency yesterday when I talked about Coulson-Fisher. Right, when you went far away, the wave function changed. Where the energy function should be such that the mu changes. That's the DFT language. Alright? So that's, now obviously, if they come close together, then this becomes plus and minus. You gain in the electrostatic energy. If that electrostatic gain energy is enough to overcome I minus A, then you have a transport. That's how you make the energy model. Okay? So we have changed from that wave functional language to DFT language. DFT language is in terms of density, it's in terms of the derivative of the energy in terms of the density, it's in terms of chemical potential. Right? So this is, like I was saying yesterday, from microscopic theory I have gone to a theory which is like fluid with continuum. But you have to change the language. Is that okay? That's why when you're developing this theory, you have to do this. 2 minutes? Okay. So I think I can stop here. Okay, just last point. Now this is fine. What about KS system? The Kohn-Sham system. Mu is the same, right? So epsilon max is mu. You saw that, right? If I could do a Kohn-Sham calculation with fractional number of electrons, how would I do that? I'll put one electron, one electron, one electron, and maybe a bit of it, and small. That's how you do it. I can put fractional number of electrons, 0.5 electron, 0.2, and this. If I do that calculation, then as long as the number of electron is in that fraction, epsilon max, should remain a constant if you have an exact functional derivative. If I'm doing a Kohn-Sham calculation, and suppose I had the exact exchange correlation, exact, then epsilon max is mu. Suppose I do a calculation with number of electrons, x with n plus f, which is between n and n plus 1. Right? As long as I'm between these two, mu should remain constant minus I. Epsilon max would not change. They remain fixed. That's a test. Okay? I've asked you in the assignment to show geometrically, purely, I've given you all the mathematical arguments, but you taught it like this. If this condition is satisfied, geometrically, only the neighboring state will mix to give a minimum. Okay? And yeah, that's it. Only neighboring neighbors will give you a minimum to be consistent. I've given that as an assignment. I'll stop it. I'll repeat it and then we can go for the form.